Students, today the topic that we will discuss is quite simple and quite known to all of us. I am talking about motions. Any movement is a motion of a body from one place to other place. But this is a relative term, quite a relative term. A common example could be if two of you are sitting in a train, you and your friend sitting in a train, you will never find your friend in a motion. You will feel as if your friend is a non-moving object at that moment. But one who is seeing it from platform or from some sideways, he will observe both of you in motion. And that way, even if we are not sitting in a train, just you are on the earth, are you not in a motion? Yes, obviously you are in a motion. Earth is rotating around its own axis constantly. Earth is also moving around the sun in a circular or orbital kind of fashion. So we are knowingly, unknowingly, constantly in motion. Earth is in motion, we are in motion, sun is in motion and everything. This is something which is on a macro level. On a larger level you see the things moving. But even at micro level, at the level of atom, there are motions. There are electrons orbiting the nucleus, or there are vibrations in atoms. So all these motions can be studied together. And we can classify these motions in some specific kind of groups. Before I come to the classification of motions, what is motion essentially? It's a change of position with respect to, of course, time. When some object appears to change its position, we see it's in motion. Now, to understand the change of position, we often speak in terms of distance that object has moved from one place to the other place. But distance is little confusing term, because if I say object A and object B, somebody may take a path like this to reach object B. For that path, the distance would be this much. Somebody may prefer even going this way, so the distance would be much more than what it was earlier. So instead of distance, physics talks in terms of displacement. It is nothing but minimum possible distance joining two points. So it will be, of course, a straight line between A and B. That is a displacement. So displacement in given time, that is what is spoken when we think of motion. Now one more thing, it is the final, that displacement is about initial position and final position. If somebody goes to point B and comes back to point A, he would have traveled a lot of distance. But as a displacement, it is zero. Because initial position is A, final position is also A. So there is no displacement of that particle or of that object. That is the fundamental difference between the concept of distance and displacement. So likewise you can talk in terms of speed and velocity, but keeping that aside, because that may come sometime in Newton's physics, discussion on Newton's physics. Today we have to talk about types of motion. Now broadly, that way one can classify motions in different ways, like periodic motion, non-periodic motion, uniform motion, non-uniform motion, and so on. But as a type of motion, normally we classify them in three such classes. In some textbooks you may find more number of classes. More or less the concept is same, but the classification is different from book to book. If I think of translatory or translational motion, it can be straightway linear motion from point A to point B, straight line like a motion, rectilinear motion typically when we call it, or there could be curvilinear motion. Point A and point B, there could be curvilinear motion, or we can say further it could be even a circular motion. circular motion is, say, take an example of a analog clock. Its different hands will have a circular motion like this, or when the earth is orbiting around the sun, that is circular motion or orbital motion, or so that is a completing one circle. These are translatory or translational motions. Coming to, of course, if I have to give you some examples, one can easily find out in linear motion. Any car moving on the road straight is linear motion, or a rectilinear motion, same. Curvilinear motion. Take an example, there could be a child's small game where there is a round track and a small train is taking a kind of curved path, that is curvilinear motion. I have already spoken about circular motions earlier. So these are the types of motion which are translatory motions. When we talk of rotatory motion, it is around its own axis when some object is rotating. This is typically called as rotatory motion. For example, Earth is rotating around its own axis. While orbiting around the sun, it is also rotating around its own axis. That is rotatory motion. Or when you throw a top and top rotates around its own axis, that is again rotatory motion. Or a wheel of a car or your cycle or motorcycle, they also have this same motion. Or giant wheel when you go to a fair, that is again same rotatory motion. Several examples one can easily find about rotatory motion. What is an oscillatory? Oscillatory is motion around a mean position on two sides, like oscillating motion or vibrational motion. It could be as fine as when you strike a string of a guitar or violin or any such instrument that vibrates around its mean position, goes to one extreme end, comes to the mean position, goes to other extreme end, comes to mean position. That is the way it vibrates. So that motion is oscillatory motion. Or a pendulum moving back and forth. So basically it is a typical example of converting potential energy to kinetic energy to potential energy, back to kinetic potential. So that oscillation of a pendulum is a type of oscillatory motion. Or even for the oscillations of atoms, they are at micro level but oscillatory motions. So these are the types of motions which one can easily understand by just giving a little thought on their names and their applications. Of course, always you will never find a single motion in objects. There are compound motions or motions which are together in several objects. For example, I gave an example of car wheels. But you actually see the car moving forward. That means car is in linear motion when the wheels are in rotatory motion. So such examples you too can find out. Just to summarize, you know objects are constantly moving. Motion is a relative term. Not everybody will be able to recognize that motion. Somebody may feel it is non-moving objects, but others can find it moving with a frame of different references. So motion, as I discussed, is decided by the displacement between 2 points, object between 2 points. That displacement. Motion has several types. Some are periodic motions which keep occurring with same kind of continuity in the same time period, they keep recurring. Those are periodic motions. You will find that even pendulum motion or oscillatory motions are periodic motions, or even the Earth's orbit around the sun is a periodic motion. So there are periodic or non-periodic motions. There are uniform and non-uniform motions. One more single type, that is a random motion. Either you can classify that as one more type of motion, or you can consider it as a part of translatory motion. That is fine. So here the motion is that way like a linear motion, but however it is unpredictable motion of objects. For example, if some balloon is filled with air and you release that balloon, It may go in any direction in air without any predictable pattern. That is of course a random motion. Or gases, they move in air. If you have hoop stick, that kind of movement can be easily considered as a random motion. Or even some, like take an example of mosquito or anything, they have these random motions. You cannot make out where exactly will be the next moment of that insect. Again a random motion. Or more scientifically one can say motion in gases named as Brownian motion of molecules is also random motion. So this is all about types of motion. Now it's a time for activities. We will just see different types of motion and activities, and more specifically we'll talk about pendulum formula. Something more about pendulum I'll talk while doing that activity. So get ready for activity. Let us see different types of motions using some simple experiments or simple objects. When we talk of linear motion, you can practically show it using any object like this kind of duster, where it moves in one straight line. This is nothing but its linear motion. That can be easily seen. If I take a rubber band, stretch it and simply pluck it, this produces vibratory motion in this rubber band. Like what you can perhaps imagine, that a similar motion would be created on strings of musical instruments like guitar. So that is a vibrational motion in this rubber band. I am showing it. If I take two such wheels and connect them using a steel rod, I am essentially making wheel and axle structure. This will show you something interesting. See, if I look at this wheel and axle, if I rotate it this way, this is happening like a wheel rotating around its own axis. So it's a rotatory motion of wheels. But the moment I place it this way, and it starts moving. So wheels are having rotatory motion, but as an assembly, this is moving forward. That is, it has linear motion. So it's a compound motion. Two motions are working together. That's the way your car moves forward. It is in linear motion and wheels are in rotatory motion. Now, the last kind of motion I will show is a random motion using a balloon. I will blow the balloon and hold it in my fingers. Okay? And the moment I release this balloon, you can easily imagine that will go just in a random kind of motion. And exactly that's the term used for it, a random motion. Just take a look. We will make one analog type of clock. There are two things which will happen with this. One is, you will understand a kind of motion of hands of clock. They keep taking a circular motion in this analog clock. All hands have similar motions, but the most visible would be of course second's hand, because it completes one rotation in just 60 seconds. But same clock we will be using to count number of seconds for pendulum motion, because we know pendulum is the main activity. This is a preparation for that as well. So we have given this disc a printed sheet, this printed white in the middle. So we can, or you can, paint this as per your choice. Then this is a clock machine. We'll be placing a cell in the end on the back side of it, and these are different hands. Our hand, minute hand and second hand. So they are given two, one extra is given because sometimes this stem, small stem breaks in the fitments. So one extra is given, spare is given. Let us begin. First remove this threaded cap along with this black colored round disc from this assembly. Take out this washer type of black cap as well. Press fit this from back side, bring it to the front. This middle portion comes to the front. Put this black disc as it was. We'll just place this car sheet first. And then place this black disc as it was, and this kind of nut on top of it. You can just tighten it using your fingers. You don't need any additional tool for it. Okay, once it is tightened, we'll start with different types of hands. Now the lowest would be this hour's hand. Remember, I have taken this curvy surface of this hand on top and I am pressing it down, so it will get fixed there. So yes, it is fixed. Then on top of it I have to fix this minute's hand. That is also fixed. So they are independent motions. And on top, in this small kind of hole here, I must insert this stud from second's hand. This is a very small fine stud which I must fix on top of it. That's the way your clock is ready. I just will take a cell and place it so we can check it. On the back side, you can easily see there is plus sign and minus sign in this area of cell. So this minus negative terminal goes here, and I fix this tightly. So first start with positive terminal like this and then push this negative inside. Once you do this, you will find the clock motion has started. Now I can set time by rotating these hands. So I have adjusted the timing. Now this won't stand just like this. I must do something about it. We'll be using this metal clamp to make sure that this stands, and while using this also a care should be taken that this does not obstruct motion of these hands. So keeping 12 on top, I'll just place it this way, straighten these two sides. So these two arms of this clamp, they are straightened. So they rest on two sides, giving this enough support, and this clamp is locking onto this dial. But make sure that this clamp does not come on the path of these hands. So your clock is ready. Now you can decorate it the way you want, make it something very special for yourself, and keep it on a study table always. Let us talk about pendulum motion. What is a pendulum? It is nothing but a mass tied to a thread of some negligible mass, a thread which does not have much mass. So that thread and a bob, typically this is called as a bob. This is called as a bob. Thread suspended to a support. So around this pivotal support, this pendulum can go on one side and also can go on the other side. So this is nothing but its oscillation. So this is mean position. From mean position it goes to the highest point. So it has maximum potential energy now, and it comes down or descends due to gravitational pull, comes back to mean position, goes to the other extreme high, again goes to the maximum of its own potential energy, and then comes to kinetic energy and comes back. So one complete such rotation is called as one oscillation or one period of that pendulum. This is called as one period or one oscillation. Now, to know something further, let us understand it clearly that this is a total distance that this pendulum has to travel. If a pendulum travels less distance, say if it travels only this much of distance, will it be faster than this? Will it complete its period faster than this? No. The period remains same even when the distance traveled by pendulum is less. So the period of pendulum depends not on mass of this object. You can suspend a bob with 1 kilogram or maybe just 100 grams. Still the result will be same. So the period is independent of mass. Period also does not depend on the amplitude, that is the height of this pendulum swing. Even if the swing is from lower height, it takes same period. Of course, this is true for some limited kind of range of amplitude. If amplitude goes higher and higher, then the period may marginally increase. But for a limited kind of range, the period does not depend on amplitude also. Then what is it that the period depends on? That is nothing but length of this pendulum, L. This was discovered by a great scientist who did lot of experiments on different topics. Name of the scientist is quite known. It is Galileo. Galileo found out when he was doing his prayers in cathedral or a church, he found that the chandeliers which were suspended from roof, they were swinging due to wind that was coming into the church. They had long kind of strings, so these lamps, they do swing like this. He always kept observing those lamps using his pulse. So he always found that the period of these lamps did not change even when the amplitude was small, or even when the amplitude was large, it showed same period for a certain length. So right in the early part of 17th century, in 1602, he was observing this for several years. But in 1602 or 1602, he then put forth concept of pendulum and its relationship with length. That was a contribution made by Galileo early in 17th century. That was taken forward by a great scientist of same century Huygens, he established a lot of science around this pendulum, designed first pendulum clock, and wrote a complete book about science of pendulum. That pendulum clocks, perhaps some of you might have seen nowadays in museums, but earlier they used to be on walls of every home. So that pendulum would keep moving, and being the time taken by pendulum's motion would never change. The time shown by a clock will also be very accurate. The accuracy was achieved at that time to the extent of 1 second difference per year. That was as accurate as that. And for almost 250 years, pendulum clock was used by scientists to measure the time. So you know there is a universal time measure, or on earth the time is measured constantly using some kind of device. Till 1930, pendulum clock was in use. In 1930, it was replaced by quartz kind of mechanism, or vibrations of quartz crystals. But that came as a new science then. Till then, this fundamental concept was in actual use. Following this Huygens, then a lot of research then went into that. Robert Hooke designed a conical pendulum and tried to establish, or he shared that with Newton, how exactly gravity of planets work, or it works. So for establishing universal gravitation, something which is not for you right at your age, Newton used that research made by Robert Hooke. See, just to know why I am sharing such a story with you is, any topic in science develops gradually by contributions of so many scientists, and finally that concept takes a complete shape. Like nowadays we talk of Newton's laws of motion or Newton's laws of gravity and so on. That is based on several such concepts. Now coming to the relationship of pendulum period, let us call it as T. T is a period. The relationship states this way: 2 pi. You know pi has a specific standard value, that is 3.141. I will not share much about this right now. And this has L by G. G is acceleration due to gravity at a specific place. Usually we consider that as 9.8 per meter per second square. So that is the acceleration due to gravity, G. We consider it as constant, however it changes from place to place. That too, actually the changing gravity or acceleration due to gravity from place to place was also discovered by using pendulum initially. So pendulum has helped us in understanding basics of gravity, basics of measurement of time and so on. So this is a relationship. If I, for simplicity, make square of left side, square of right side, then it will be T square is equal to 4, because 2 square, that is 2 into 2 is 4, pi square L by G. This could be the way we can find out square of period, square of T, and then you can find out actual T. Now look at this pendulum formula. The period T is equal to 2 pi in square root of L by G. You know that pi is constant, its value is 3.141. G is constant for that particular place. So the period or T depends on value of L. More the length of pendulum, more will be the time taken for one oscillation of pendulum. So more the numerator in this will not change. Only changing L will decide the period. So longer the pendulum, more will be the period. If I take length of pendulum, if this is a pendulum, if I take length of this pendulum starting from its pivotal point and up to midpoint of this bob, that's the length. If I take 1 meter length, exact 1 meter length, then the time period will be exact 2 seconds. So this is called as a meter pendulum. So if I reduce the length, the oscillations will be fast. If I increase the length further, naturally it will be still slow. It will take more time to complete one oscillation. Right? So let us do now experimentally, we'll try to see time period for different lengths of pendulum. By changing length, how exactly this changes, and we'll every time see does that match this formula. So we'll try to do this experimentally. Okay, so get ready for activities around pendulum. Let us prepare a pendulum. This is the pendulum bob. As I told you, this swings back and forth. First, tie one end of thread to this. This thread is longer than 1 meter because we have to go up to 1 meter's pendulum. Pass the other end of this pendulum through a batten. Batten has a hole. Now what will we do? We will start with a simple reading of pendulum, or actual oscillations will measure of the pendulum whose length is 25 centimeters. Now from this lower end of batten, I must take length up to midpoint of this ball. So ball has this circle which is showing its midpoint. I must take 25 as a length of it, and we'll be using this clamp or this cloth peg to lock this thread like this. So this becomes a temporary grip of this peg on batten, and this does not move. Then what will we do? We will place this batten on some support or some platform, put some big book on this, so this does not move, and then we'll swing it. That's the procedure which we will follow. But prior to that, I must first make sure, I must do it that I should measure 25 centimeter for length of it. So I am taking centimeter scale. So here is 25. Yeah, this is 25. Correct, 25 I have taken. I'll just lock it using this clamp. Once again we'll measure up to the midpoint. It is coming as 25. Okay, likewise we'll go for 100 centimeters as well, but let us first start swinging this pendulum, and we'll go for 10 oscillations. We can start from some points, for example one end. Let first 2-3 oscillations we can ignore, and then we'll start counting 1, 2, 3, likewise up to 10, and we'll record that time on board, that how long did it take to complete 10 oscillations. We'll repeat this reading 2-3 times. Always in scientific experiments, you must repeat at least 3 times and take average of it. we have prepared a setup. You can see this is we have created this setup, a freely suspended bob, or this is a pendulum. Right now its length is 25 centimeters. It can swing without touching any of the surfaces, and we have to count time taken for 10 such oscillations. So I'll just begin. We'll use this clock to count number of seconds. Let us start observing it. I'm releasing it. See, never pull it up like this. No, you should release it from just some angle. I'll release it now. Let us start counting. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it took exactly 10.5 seconds. I'll go for second attempt. I'll release and start counting. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It took 11 seconds. We'll go for one more count. One was 10.5, other one is 11. We'll go for one more attempt and then take average of it. I can write these readings here. It's 10.5, 11. We'll go for one more attempt. I have released. I'll start counting. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it stopped here. So again 10 seconds. So average is 10.5 when the length is 0.25 meter. We have created setup for 1 meter length of pendulum. So starting from this lower end of this thread up to half of this pendulum bob, the length is exact 100 centimeters. Now we will just pull this bob a little bit and release it, and we'll try to take figure for 10 oscillations, the time taken for 10 oscillations. Let us start, and then after 1 or 2 oscillations we'll actually start counting. We'll start counting now. 1, 2, 3, 4, 5, 6, 7, 8, 9 and 10. Yeah, so we have done it. The figure is 22 seconds. So 1 meter, the first reading is 22. Let us repeat this process again. I am releasing this second time. I'll start counting now. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 21 seconds. We'll go for one more reading. I'm releasing this again. Let us take as 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Again it came to 21 seconds. We have taken these readings when the length was 0.25 meters. The average time for 10 oscillation came out to 10.5 seconds. If I convert it to time for one oscillation, it will be 1.05 seconds. Whereas when I took 1 meter as length, average was 21 seconds for 10 oscillations. By dividing this by 10, I get 2.1 seconds per oscillation by actual observations. So this is your experimental results. And how about the results from formula of time, or T is equal to 2 by square root of L by G? That is the pendulum formula. Let us try first for figure of length of 25 centimeters or 0.25 meters of pendulum. So 2 into 3.141 in square root 0.25, that is the length in meters. 9.8 it's G, value of G, and if I solve this, you will get the period of pendulum having length of 25 centimeters or 0.25 meters comes out to 1.00. So it is 1.003, but if we take only 2 digits, it's 1.00. So a pendulum of length of 25 centimeters completes one oscillation in 1 second. Now going for pendulum with length of 1 meter. Again, if I place everything in formula, 2 into 3.141 square root of 1 by 9.8. If I solve this, the figure comes to 2.007. If I ignore third digit, it's 2.00. That means if the length of pendulum is 1 meter, exact 1 meter, one oscillation takes 2 seconds. So that means pendulum going from one end to the other end takes 1 second and 1 more second to come back. So it is called as seconds pendulum. One side is completed in 1 second, second side is completed in another 1 second. So 2 seconds for one oscillation. That's how you can find out, taking different length. Say for example, you can take 40 centimeters, find out, or 0.4 meter, find out what is the period for that length, and each time you will find that experimental results and results coming from calculating based on formula, that is your pendulum formula, will give you almost same result. That is the beauty of science and mathematics working together. This experimentation is a part of science, and this is how you can solve it using mathematics.